So welcome back to one more presentation on our PLC systems. In the previous presentation, we have seen some of the examples of the data handling instructions, wherein you have the data movement, then the data comparison, then you have the arithmetic operations, right, which are permissible in some of the PLC systems that we have seen, right? So now moving ahead in today's presentation, right, let us look into something of what is very important is closed loop control systems as applicable to PLCs, right? So if you start with an example, right, generally may not be the case in the Indian context, in the Western countries and all, the room heater. This is one very widely used thing there, right? So basically you have the thermostats there. As long as your temperature is in a very comfortable zone within this, right? So you have to maintain it. Whenever it goes below this, you have to increase the temperature. Whenever it goes above this, you have to decrease the temperature. So here the temperature is increased, here the temperature is decreased, and so that you maintain this temperature all the times depending upon the requirement, right? So this is one system wherein you will have a kind of closed loop control, right? So the adaptive control, what is the meaning of adaptive control? Whenever you are driving a vehicle or whenever you are riding a two-wheeler, right, suddenly if some dog comes across or a cat comes across, what you would do, you will apply the brake. So that is called as the adaptive control. Right, your brain quickly thinks that something is there, and you close the, or you take the instantaneous action there, right? So a similar thing, right, this is as per the what you can call as the uh, activation of the neurons in our brain or something like that, because we have got the natural thinking ability to do so, right? But whenever you want the machines to do all these things, you must have some mechanisms developed so that you make use of a closed loop system, wherein you generally deal with input, output, and feedback signal, right? So this feedback signal, right, generally creates what you call as the error signal. But this error could be a positive error or could be a negative error, so we call it as delta in our general convention, right? So this, depending upon this delta, so we would be able to either increase the input or decrease the output in order to have the required outputs. This is what is the basic theme that is involved in your closed loop control system. And accordingly, in order to implement the closed loop control systems, what are the different things you need, all of you know, right? So let me give you a simple diagram of this, which all of you must be very familiar with this, right? You have something called as a controller here, then you have called something called as the actuator here, right? So you have the process here, what exactly you are doing there, right? So then you have got some output, then you have this feedback in the form of, say, measurement. I would write all these things, right, and that would go somewhere here. So this is my measurement here, this is my measurement block, right? And this is my, you say, controller. This is my controller. Then this is my actuator. This is my actuator, and this is my process here. Right. So, you would have, so some kind of output here. Here the measurement, right? And here you will have something called as the set value, as all of you must be very much familiar with this. And here I have the actual value, right? So this is where you generate the error signal here, and this will help your controller to decide what exactly it has to do, and accordingly you would be able to maintain a required output at the uh, appropriate place, right? So the set value, or even I can take it as the input here, either input or set value you can take. So let me take this as plus here. Generally we use the negative feedback systems. So this is the general structure, whichever system you take, right? Could it be a physical system, could it be a mechanical system, could it be an electrical system, or could it be electromechanical system, whatever it is, right? So this is a general system or general structure, how you would see it, right? And generally here you would have these, the feedback path. This is the feedback path. Okay. So now, after having seen this, you can definitely consider this as one of the applications what we have seen earlier, temperature control, or any kind of the closed loop control system based applications, right? So now, if at all you want to deploy the PLCs, right? If at all you want to deploy the PLCs to say control some kind of industrial process or some kind of action, right? So basically, the remaining parts here, whatever I have shown, right? So could it be the actuator, right? Could it be the process, or could it be the measurement? All these things remain same, but this particular portion now I need to replace by those blocks corresponding to a PLC. So how would you see it? How would you look at this particular thing? Now what I will do here is I'll just remove this. I will remove this, and this portion I would replace by PLC system, right? Something like this. Something like this. So this would go here. This would go here. And here I will have ADC. Here I got DAC, and this is my PLC system. And here, this is my set value, as I I've already shown you it earlier, and this is my, say, I will make a small change here. This is what is my actual value, right? So this is the one what you can call as PLC for closed loop control. This is what we call it as PLC for closed. Other things will remain same, right? So now when I use the PLC, my focus will be on PLC now, right? So far we have seen the different kinds of operations that your PLCs are able to perform by looking at different examples, right from your ladder diagrams, the conventionals, conventions, your functional block diagrams, right, or your structure text, internal relays, or timers, counters, shift registers, and all these things, right? So even some of the data handling, instructions we have seen from the point of view of PLC. But when I come to the operation of the PLCs, as long as a closed loop control is concerned, right? So let us try to see whenever I go with the closed loop control, right? What are the different modes of control? That is very important for me to understand. Modes of control, because I need to use my PLC within for the system within the different modes of controls available to me, right? So whenever I speak about the modes of control, we generally come across three things, which probably all of you are very much familiar with. One is called as proportional control, or which is also called as P control, which is a very simple and basic primitive type of control, right? Wherein your output will be some constant into error. So this constant we generally call it as KP, constant of proportion, right? So now this is again, if you get the representation of this, right? So now here take this as output and this as error, it would be a straight line like this, right? So this is the simplest form of the modes of the control you can have, which is the proportional control. But the problem with the proportional control is that it basically has got the lag, okay, the basic lag in the system, right, because of the very nature of the system. So therefore the output generally oscillates before it reaches the final stage, right? Whenever we speak about the mechanical system or electrical system, right, because of the inherent inertia, right, whenever you want to take out the output which is just proportional to the error and some constant, it is always bound to have some kind of oscillations. So therefore in the sophisticated system design and all, generally the proportional control is not preferred, whereas you go with some other versions of the control wherein we have the output, the controller output is equal to some constant and integral of error signal. So these things you already studied in your control systems and all, right? So by making use of the integral, right, we generally make the system to respond in a faster way, because your signals, suppose if this is the error signal and this time, your output or the controller output would become like this, and it covers area under the block of the error signal, right? So this is the better way. Whenever you take the integral of the error signal, right, it covers up the things in a better way, and you are going to get you are likely going to get the less oscillations, and your control will be accurate. And apart from this, if you want to have one more kind, that is the controller output, which is some constant. Previously also I have not mentioned what is that particular constant, and is considered to be the rate of change of error signal, rate of change of error signal. This kind of system gives you still better the output characteristics or the better controllability, right? So now we can take this as kd into error signal. Previously also I would take this ki into ESS. So now when I come here, suppose if my error signal is something like this, this is error, this is time, and here as long as your output signal is concerned, you would get the signal like this, right? So now when you combine all these things, whether it is proportional, which is a very primitive but has got its own issues, when you have got integral, when you have got derivative, when you combine all these things, right? So you have what you call it as a PID controller. In most of the control applications, you have the PID controller, which has got the output signal not only proportional to the error signal, but also it is proportional to the integral of error signal and also the derivative of the error signal, so that the response no longer remains sluggish and you would get the accurate output, provided you have designed the system parameters in a very appropriate manner. It is very essential for you to select the values of Kp, Ki and Kd, and accordingly you have lot of design aspects to be considered. That's a different thing altogether. But when you have this PID controller, you expect the fast and accurate controllability in the closed loop control system, right? And accordingly we have a PID controller with PLC. That is very important. Since we are discussing about the PLC, we should know what exactly is a P control in PLC. Your most of the PLCs, whatever we have commercially as of now, right? So they support this kind of PID control operation. After having seen what exactly is the constant with respect to the proportional control, integral control, and derivative control, right? Let us try to have the structure of this PID controller as per as your IEC 1131 bar 3 standard is concerned. This is as per IEC 1131 bar 3 standard. So now you can You can just note down this diagram. It's a standard representation of the PID controller. PID here. Then you have about 8 pins here and something called as this. Now these each represent, you can quickly write these things. Auto, this is PV, preset value, SP, then this is X naught, KP, TR, cycle. In fact, I should have written TD here. TD. Then comes the cycle here, and this is X out real. So these are, one is the Boolean value, and all these are this is also real, 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 real. I'm using little shortcut here, and finally this is the time. So this real or analog values, Boolean, this SP stands for set point, process variable PV. Let me do this here.
So this is how you will have the PLC control, PID controller in your PLC. So depending upon your requirement, some of the constants, your derivative or your integral, right? So you can either include or exclude. So as long as you keep things inactive, this will remain only as the proportional control, right? So if you keep only active, it will become proportional and integral control, PI control. If you keep all these three active, right? So it will become a PID controller, right? So now the respective points wherever you want to have the connection, right? Like whatever I have shown you, the process, the actuator, the output, measurement, preset value, right? The error signal. Depending upon that, if you connect those things to a different points here, you should be able to get an accurate control. Of course, this requires the program to be written. So the program will be written again as per the architectural point of view of the different PLCs. And once the program is written, right, so you should be able to have the deployment of that particular PLC for the closed loop control. So now, as of now, we do not have any specific examples for having the closed loop control. Our examples or our applications, whatever we are supposed to discuss, they are based on the basic functional blocks like your timers, shift registers, counters, maybe your master control relays or internal relays, or even some of the conventional ladder diagrams, right? So with the help of those functional blocks, the basic functional blocks of your PLC, let us try to look into a few applications with some case studies and all. So after having seen those applications, that's where our discussion virtually ends, right? So however, there are so many scopes, additional scopes for you to get into these things, because since it is a 3 credit course, we have the time restrictions here. So we have not gone into the actual the software part and the real time implementation of the PLC projects, right? However, if you are comfortable with the PLCs, definitely you can make use of the services available at our college. We have got, most of you may be knowing that we have got the Bosch Retrox Center of Excellence, where 4 or 5 PLCs are there. There, along with that, you have got the corresponding softwares and the hardwares. Some of the additional auxiliary circuits are there, simulators are there, emulators are there, right? So you can definitely develop your own applications. But since we have not studied anything about the Bosch PLCs, it is essential for you to look into those configurations or those syntax of Bosch PLCs, and then you proceed, and that becomes really easy for you because we have already been understood some of the basic concepts or the basic principles that your PLCs carry. Once you know that, maybe as long as the implementation is concerned, so that will slightly change from PLC to PLC, but the very ladder diagrams, right, the logic or the sequence of operation, the using of the bits, using of the input switches, using of the output switches, all those things will remain same. They will not change as the PLC manufacturers manufacture different type of PLCs, right? So with this, I will stop here. In our next discussions, we will basically concentrate on some of the applications what they are mentioned in your syllabus. And after having seen those applications, I will give you some of the simple assignments based on that, which you need to
carry out. So with that, I will stop now. If you have any doubt here, please ask.